Today we are going to do section 5.7. So please look at page 608 where we're going to look at the inverse, the the derivatives of inverse trigonometric functions, or let's say the results of them. Now the inverse trigonometric functions, when we have already taken the derivatives of them, and the result is the stuff under the integral we're seeing. So we're not going to prove these things, but rather directly go to use them in an example. Now the first one you can see is the integral of, let's look at example 5.49. The integral of 1 over dx over 1 minus x squared. See, that is a very simple problem. And then when you look at this, then you flip over the old page and see which one looks like it. Then you notice that is the very first one. See, the first one, if you let a equal to 1, then the problem looks just like that one, and the answer is you directly apply the answer is sine inverse of x, and being that a is 1. So please do that example, and after you did it, being that this is a definite integral, you have to evaluate it, which is in this example is very simple. So I'll write down example 5.49. So next, let's look at example 5.50, where we have to integrate 1 over 4 minus 9x squared. Now that you recognize is in this form, okay? The minus is important. If it's plus, this is not going to work. Everything has to be exactly the same. So a squared, where a is 2. So remember that a equals to 2, and then u will be equal to 3x. All right. And with that, then you can plug in the the formula to directly apply. Now that would be the same as so we do the same substitution as we have always done. U equals 3x, then du equals to 3dx. Okay, dx, and I'll write the 3 down here. Du equals to 3dx. And then and now that we're all set, we plug everything back in here, which is all right. So dx is du over 3. Write that over here. And then u is a is okay. We write down that equals a is 2, so 2 squared minus u squared, right? 2 squared minus u squared, so it looks exactly like this form. And that's about it. We have everything taken care of. Then we apply this formula, which says this equal to sine inverse of u over a, which is 2. Okay, a, we only pick the absolute value, just means we pick the positive value, which is what we always do anyway, and that's about it. But that's not all. Okay, where's my 1/3? Right? No, it's not 2, it's 3. Okay, and that equals to 1/3. What am I doing? Wait a second. Sorry. The 1/3 is over here. Okay, that's just the number. And then the formula says is inverse of u divided by 2. Sorry. Like that. Okay, let's apply the formula reasonably. And then that is, which then equals to, we'll plug the u back in. U is 3x. So it's 1/3 sine inverse. U is 3x. And then divided by 2. And that should be it. And then never forget that constant. Whenever you do indefinite integral, add the constant. Because within the constant, when you take the derivative of this, you'll end up being that. Okay, regardless of what constant it is. So it's an entire collection of functions that will become that. That's why it's called indefinite. You got a lot of them to choose from. Okay, so that's that. And next, let's next, this is just evaluate the next example, example 5.51. You are evaluating a definite integral, which again, that's a very straightforward, direct application, no changes, no substitutions. So please do that as your homework. Now we've done so far the sine, cosine, tangent inverses, okay, which creates nice little formulas for us to follow. What about the cosine, cotangent, cosecant? Unfortunately, they don't really come up with much. As you can, this is in Appendix B of your book. As you see, the cosine just equals to the negative of what sine is. It's exactly the negative. And if you compare it, and so does the cotangent is negative tangent or something, and then the cosecant end up being the negative of secant. So they're not much useful for us in terms of integration. Therefore, we will move forward to the next part. Next, let's look at example 5.52, where you have the integral of straightforward 1 plus 4x squared. If you look at the formula, that would be the tangent inverse option, where you substitute u equals to 2x and a is just 1. So it's a straightforward work. So please do that as your homework. And the next example 5.53, again, is similar except in this case a equals to 3, and you don't have to substitute anything. Just plug in a equals to 3 and the answer pops right out. Next, example 5.54, a similar situation, I think. Yeah, this one, a is just 1 and you don't have to substitute anything, but you do have to evaluate it. So please evaluate this thing and make sure the math comes out, and then if you don't make any mistakes, then the answer should pops out right away. So that marks the end of this section. It's a short little section, and we will then do homework. The homework is on page 113. Please do problems 395, 99, 405, 11, 13, 23, 27, 29, 31, 33, 35, and 38. And when you get back, I will erase the board and talk about some of the problems. Now that you're done with the homework, let's talk about some of the problems. First one, I want to talk about number 411, which you have the integral of inverse and then the square root of a bunch of stuff that looks hard until you realize that all you have to do is substitute u as sine inverse of t. In that case, du will be dt over square root of 1 minus t. Okay, and then the whole problem will become a piece of cake. And similarly, for 13, same principle. You just let u equal the tangent inverse of 2t, then du will come out very nicely with an extra 2, which you will take care of by dividing du by 2. That will fix it, right? And that will take care of for 13. So the next problem we will look at is 423. The problem 423, where we need to integrate e of t over the square root of 1 minus e of 2t, etc. Now, how would you do that? There are probably various ways of doing it. I guess the choice I made is just let u equal to e of t, which seems to work out pretty good. Now, let me show you what I mean. If you let u equals to e to the power t, okay, and then du is equal to e to the power t dt. There might be a different way. You might do it differently. As long as you get the right answer, that's all anybody cares. Okay? And so du, sorry. Where's my du? Okay, du is equal to e of t dt, and then which is this part. Okay, that's taken care of. And so then we rewrite the formula and becomes du. Okay, the only thing left on top is du because that represents et dt, and on the bottom we'll have the square root of 1 minus u squared. Okay, u squared. That's the formula. That's properties of the exponent. The 2 is the same as u 2t, and then we have, and at this point we're ready to apply the formula for this thing, which is the formula of this is just sine inverse, right, of u, and then you add some constant. But before we add the constant, let's stick what u is back in there, which is sine inverse e of t, e. Where's my e? Okay, which you call the sine inverse e of t plus c. And that's your short and quick answer. Okay. And then, so that's that. And let's look at next problem. Now, problem 425 has a slight complication in that there's an extra t outside, which actually turns out to be a blessing because the natural log of t, when you differentiate the natural log of t, it becomes 1 over t. So which means if you let u equals the natural log of t, 425 right there, then du becomes dt over t, and everything's taken care of, and the answer pops out in one line. Okay, so that's 425. Next. Now the next problem looks quite complicated until you realize that what I just showed you, I'll show it to you again. Look at rule number 18, where the derivative of cosine inverse is equal to negative 1 over 1 minus x squared. So once you let u equal to the cosine inverse of x, everything will fall out. And with some adjustment of numbers, the constant multiplier, and everything should come out right away. So now let's look at the next problem, 429. So for problem 429, we're supposed to integrate from 0 to 1/2 tangent of inverse sine over the square root of something. That sounds like, wow, that looks tough. Well, it looks tough until you realize that this is just the derivative of sine inverse, which means if you let u equals to this will become du, and everything will come out nice and neat. So let's do that. We'll set u equals to sine inverse of t, and then du will be then 1 over the square root and stuff, dt over square root of 1 minus t squared. Okay, so far so good. But being that we're doing the definite integral, we got to figure out where the numbers go. So let's find out. When t equal to 0, u equals to sine inverse of 0 is 0. And when t equals 1/2, u equals to when is sine equal to 1/2? Let's see, what do I have here? Okay, sine value is 1/2 when this is 1 and the hypotenuse is 2. And that would be square root of 3. But in any case, that's the 30, 60, 90 degree triangle, so we have pi over 6. So then u will be equal to pi over 6. Okay, that's just a familiarity from trigonometry. Then next we have, so far so good. Then now I think we got it set up, right? So let's rewrite this formula in terms of u. Then we get first from 0, u equal to 0 and t is 0, to pi over 6. Yeah, don't forget to change these things, otherwise your answer will be garbage, even though you got it right most of it. And then this is tangent u, which take care of tangent of sine of this, and then du is all the rest of it. So just tangent u du, and so as long as we integrate tangent u du, we should be fine. Okay, what is the derivative of tangent? Well, let's now the integral of tangent is not that obvious, so we have to figure it out. So here's what we're gonna do. That we'll rewrite it as pi over 6. Tangent is sine over cosine. Sine x over cosine x. Sorry, not x, u. We're doing u. Okay? It doesn't matter what you do. Okay, x, u, they're all the same. So we will do u and du. Now at this point, we're gonna do another second substitution. So this time being that we'll call this variable u, the new substitution, let's call it w. So w is, let w equal to cosine of u. Then we pull the same trick. Okay, different variables, same trick. We're just calling the variable by a different name. So then dw equal to minus, derivative of cosine is minus sine, and then minus sine u du. All right, and then we'll write down the negative sign down here, minus, or over here, whatever. And then so that negative dw is positive sine u du. And with that, we can plug everything in. No, we can't. We still have to take care of this because we're transforming variables. So we're going to change the endpoint, make it come out. So when u equals 0, the bottom limit, w equals to cosine 0, which is 1. When u equals to pi over 6, okay, that's 30 degrees. Cosine 30 degrees is square root 3 over 2. Okay, now having done that, now we're ready to plug it in our second substitution. So we go from 1 to square root of 3 over 2. And then what does this become? This becomes w is cosine u, so that goes on the bottom. Okay, and then sine u du is just a negative dw. So that will go on top. Now we have a very simple integration, which is 1 over w. That's the natural log. So that equals to negative natural log of w evaluated at 1 to square root of 3 over 2. Yeah, don't forget the negative sign. If you forget it, then you get a problem. And then now the natural log of 1 is 0, so that disappears. We only have to worry about that. So the answer then is negative natural log square root of 3 over 2. Now that looks like a neat enough, good enough answer, except that when you look, if you look at the answer of the book, they give a somewhat different looking answer. And so we'll do that. And how are we gonna do that? By by this, that this equal to, so we'll do some algebra here. Okay, so that equal to minus natural log, what is that? That is, where's my 2? Give me a second. Okay, so we'll do some manipulation here. That would be the square root of 3 over 4. Put the whole thing in the square root. Okay, and that equals to, I'll write it over here. That equals to minus, we'll take the square root out, minus 1/2, what? Yes, 3 over 4. Natural log, please. ln. And then equals to, oh yeah, and then we'll stick the minus sign back on top, on the inside, which flips the fraction around. So one more step, and we'll get to the answer in the book. So 1/2 natural log 4 over 3. And that is the answer in your book. Is that important? No, not to me. It's not. But to make the answer look like the end of the back of the book, that is what you have to do. So next, problem 431, which again looks very complicated until you realize that if you let u equal the tangent inverse, like 31, if you let u equal the tangent inverse, then du will take care of the denominator, and everything will go back to just integrating the sine u du. So the answer will come out nicely. Now let's look at the next problem, which is all right. Next, let's look at problem 433, where it says for a bigger than 0, so you have some numbers here, we're going to calculate I of a. Which is integrating this thing from minus a to a. Now that is, now look at this graph. Okay, this graph I believe is looks something like this. You can plot it on the decimal graphics calculator. When t equals 0 is 1, and when t goes anything bigger than 0, it's going to die slowly. So the whole thing goes like this. It's kind of like the bell curve. sort of. And it just you go to a hump, and it's symmetrical on both sides because it's an even function. See, if you put a minus number here, the value is the same because it got squared. So then so we have this thing, and then as t goes to infinity, being that it's a fraction, as t goes to infinity, then the whole thing will go to 0. So this is the graph is approaching 0 on both sides, but it will never quite reach it though. So therefore it will not cross it or cross the x-axis or anything. And that's basically what the graph looks like. The first thing you notice is well, anyway, it doesn't matter if you notice it, but I should mention it that this is being that it's an even function, you can just integrate from 0 to a and then multiply by 2, or you can just do it like this, and it doesn't make that much difference. And then so we need to calculate this thing, and that being the tangent formula, okay, in our section. Let's write that down. The tangent formula is, what is this? 433 right here. Okay, that the integral of this by using the tangent inverse formula for integration, that equals to tangent inverse, yeah, just tangent inverse of t. Not much to it. Okay, there's no complication, no extra numbers we have to think of. And evaluated at minus a and a, which just equal to the tangent inverse of a is just, well, we don't know what a is, so tangent inverse a is just that. And then, as I mentioned earlier, the tangent of minus a, the tangent inverse has a property of tangent minus a is minus tangent of a. So subtract negative tangent inverse of a. So you have two of them. Okay, so the actual answer is you have two of them. Like I said earlier, this is an even function, so you might as well integrate from 0. So you add two of them together. So that equals a 2 tangent inverse of a. And so far so good. Now that's our answer, being that we don't know what a is. Now the question is, what happens as a goes to infinity? As a goes to infinity, what does tangent go to? Now for that you have to remember, what does the tangent inverse graph look like? The tangent inverse graph is the regular tangent graph reflected across the y equal to x line. So here's the regular tangent graph, okay, where it has an asymptote at pi over 2. So then this is pi over 2. This is the regular tangent graph. So the inverse tangent, you reflect this thing across the y equal to x line. Yeah. So then or you can just plot this thing, right, and not worry about what does this thing look like. So you flip this thing around, it looks like this. You flip it in your mind, or just, well, yeah, flip. And anyway, the inverse tangent does this, where there's an asymptote at pi over 2, and then yeah, there's that. So in other words, as a goes to infinity, the inverse tangent goes to pi over 2. So tangent inverse of a is gonna approach pi over 2. And then when you have two of them, the whole answer then will go to pi. Okay, 2 of pi over 2. And that is the right answer, which means the area under this curve that we started with, okay, 1 over 1 plus t squared, even though both sides goes to infinity, it doesn't ever reach, so it's a very long, it's infinitely long area. Its total area is only pi. If you add it, yeah, going all the way to infinity, accounting for all points under it, it only approaches pi. But it's a limited area, even though it has infinite dimensions, which makes for an interesting plot. Okay, so next let's look at problem 435. Next, let's look at problem 435, where we need to take the integral of 1 over 1 plus cosine squared x. Now that is going to be one hard nut to crack, because for this we can let u equal to cosine x, but the problem is we have to have the du, which has to be sine negative sine x dx. So we need a sine x on top to take care of the matter, and there is no sine, so we can't do that. What are we going to do? This is, we cannot, one of the formulas we learned this is the tangent inverse, okay, is 1 plus x squared. But this is an x squared, is cosine x squared, so that's a goner. And anyway, your regular tricks don't work for any of this. So your book, being very nice about it, gave us a bunch of hints. Number one, the book says you don't let u equal to cosine x, you let u equal to cotangent x. And you're thinking, and plus you put a square root 2 there too, to make sure everything comes out. And you're thinking, why would I choose u as cotangent? There's not even a cotangent there, right? And not even tangent, not even anything, just the cosine. Well, but being that we're desperate, we will accept the book's suggestion, because we sure don't know how we're going to go about doing this. Okay, and the next thing the book says, remember that the trigonometric identity of 1 plus cotangent squared equals to cosecant squared. That comes from the sine squared plus cosine squared equal to 1. And that's just another form of saying that. Okay, fine, we'll do that sometime. And the book has yet one more suggestion, hint, which says that we need to multiply this thing top and bottom by cosecant squared. Okay, one last hint, which we will follow, being that we're desperate, right? So one last hint, so that this thing becomes 1 over 1 plus cosine squared x, and then we'll multiply it by, what did it say, cosecant? Yeah, cosecant squared, csc squared x, csc squared x. Okay, top and bottom same thing, which means we're not changing anything. That's just 1. All right, dx. All right, so far so good. But okay, now that looks pretty decent, except that we're supposed to let u equals the cotangent x. Where's the cotangent? I don't even see the cotangent. So we need to beat this thing around and hope that some cotangent shows up. All right, so we will multiply this thing out. Let's put some parentheses here. And then we'll multiply this out. This equal to we'll keep the cosecant on top, squared x. And then the bottom, 1 times cosecant is cosecant squared, csc squared x. And then cosecant times cosine times cosecant. What was cosecant? Cosecant is 1 over sine. Okay? So then cosine times cosecant is equal to cotangent. Cotangent is cosine over sine. So this becomes the cotangent squared, okay, that's squared, both two squares, x. Now at this point, we finally got to the cotangent, right? So far so good. And then now we're going to do the u trick. All right, now how, is that right? Wait a second, we're not done yet. Okay, next we are going to, we're not going to do the u yet, because we're going to apply this thing. What do we want to be? We want to get rid of this cosecant so that everything becomes cotangent. So then we'll plug the cosecant. Cosecant is 1 plus cotangent, the squares, and plug that in here. So then we have 1 plus cotangent here. And then add another one, makes it 2. So that equal to cosecant, copy down the top, x. The cosecant, 1 plus cotangent, it becomes 1 plus 2 cotangent squared x dx. Okay, and then now we are finally somewhere. Okay, is that right? Yeah, now we're going to plug the u in there, because now we have cotangent down here and things will look better for us. So in the meantime, we'll figure out what du is. Du equals to square root of 2. Derivative of cotangent is let's see, cosecant squared. Okay, so and negative 2. Don't forget the negative. So the derivative of cotangent is negative cosecant squared csc squared x dx. Now in that, once you figure that out, you realize that this thing, except for the number and negative sign, it will take care of what's on top here. Okay, so we're good. We are on our way to the promised land. And then, so now we can plug everything in. First, so the cosecant, the top cosecant squared x dx right here, which is just du divided by this number. We'll write that down over here. Du divided by minus square root of 2. Okay, and then that took care of the top, right? We double check, we didn't forget anything, everything's good. So then we only have to worry about the bottom. What's the bottom? 1 plus 2 cotangent squared. That's basically u squared. All right, so it becomes 1 plus u squared. Correct? Yep. You see, that's why there's a square root of 2 here. So then that takes care of the 2. See, then we don't have to go through something again. And then u squared is this equal to this little part. Okay, that equals to exactly equal to u squared, right? U squared is that. Okay, so far, very good. Now this is the tangent inverse equation. Okay, so that being the tangent inverse equation, then we can pull out the tangent inverse and do the integration. That becomes, so the minus square root of 2 is still here, don't forget it. And then we have the tangent inverse of u, right? Okay, very good. And then next thing we're going to do, now that we got here, we'll plug the u back in. What was u again? U is this thing, square root of 2 cotangent of x. So let's do that. That equals to 1 over negative square root of 2 tangent inverse of u, which is square root of 2 cotangent x. And then plus our constant. Indefinite integral, always remember the constant. Okay, that's about it. And that's the correct answer. Okay, if you check the back of the book. However, the book then says something funny. Why? And change the answer to something else. And why do we need to do that? We don't. It's just nobody likes the cotangent. Okay, we want everything to be in the form of tangent and sine, cosine, tangent if we can. Nobody likes cotangent, cosecant, cosine. I mean not cosine and secant. Those three are the inferior functions. We want to. We just for to look good, not because it's right or not right. So if you want to do that, then you remember something like this. Okay, there's a tangent. The inverse tangent has this relationship. That is, tangent inverse of some number, any number really, as let's say, plus tangent inverse 1 over s. That happens to be equal to pi over 2. Okay, why is that? That's because of that's the same as saying if you have any right angled triangle, okay, tangent inverse of this angle, that's that one, which is a over b, okay, that's this angle, and then if tangent inverse of flipping a over b is b over a, that's 1 over s, is that angle, and these two angles add up to be 90 degrees. That's all. So this is a regular truth that normally nobody cares about. But anyway, now if we apply this situation in here, we can get something out of it. So in an attempt to look more elegant, we're going to apply this formula on this to make the cotangent go away. We don't need to, but we're elegant people, okay? And therefore, we're going to be elegant. So therefore, the tangent, just looking at this part of this thing, with the tangent inverse of this thing, okay? Square root of 2. Tangent inverse square root of 2 cotangent x, just this thing equals to what? It equals to, you'll flip it around. this equals to tangent inverse of square root of 2 over tangent x. I just, because cotangent is 1 over tangent. And then next, what we're going to do is that equals to, we'll apply this formula, okay? And that equals to pi over 2 and we'll pretend this thing here to be 1 over s. 1 over s. So then so we'll apply that formula right here. So if this is 1 over s, we plug that one in. So that equals pi over 2 minus this chunk, tangent inverse of just s. Now 1 over s is this thing. So s is tangent x over square root of 2. Like that. And now this is just this part right here, okay? And then the original formula then becomes A equals to 1 over negative square root of 2 times this stuff inside, pi over 2 minus tangent inverse tangent x over square root of 2. That looks okay so far. And then plus c. Now one more step is that you notice that this is just a number, and then there's a negative sign and negative sign here. So the answer becomes the final answer is 1 over square root of 2 tangent inverse tangent x over tangent x over square root of 2. Okay, and then this number here, 1 over square root of 2 times pi over 2, negative, etc. We will slap it onto the c, which means so the constant's different now. It's a different c, c1. And that's the answer, okay? Because c can be anything. So c1 can also be anything. Therefore, we can just call it c too. I mean, we can just call it c. This c is different from c1, but they can be any number. Each one can be any number, so it doesn't matter what you call it. C, c1, same thing. That is the final answer that your book finally dug out. Now, why do we go through this? It looks better. Your answer has only tangent in it, not something repulsive like cotangent. And mathematicians, as students of mathematics, we don't want to be repulsive. We want to be elegant. So that's where this comes in. The last problem we are going to talk about, problem 438, where we're supposed to take the integral of 1 minus t squared. Now that is not going to be easy. That might look somewhat familiar, but what we've been doing is 1 over 1 minus t squared, not just the thing itself. There's basically nothing we have that will directly give us the answer. And no substitution either. If you let u equal t, well, that gets you nowhere. U equals 1 minus t squared. That's fine, but you need a t on the outside to take care of du, and there's no t. You're missing that t on the outside. The point is you're stuck. Okay, so then, for this particular problem, however, the book is showing us a trick of how to find the answer. The answer is this thing. Look at this. That looks complicated, right? But actually, the solution sounds better than the answer. So let's look at the solution. What is the solution? We're gonna draw this thing. Okay. Now this is actually a circle. You have to recognize that. Yeah, that's the formula of part of a circle that goes, anyway, so we'll draw a circle, and the circle goes, we'll just stop here, okay? And the equation here is any point on here is going to be, we'll go from, we will stop right here and draw a line down. Okay, this point is x. We're gonna integrate from 0 to x of the part of the circle that is 1 minus t squared. And yeah, well, the fact is a circle, you just have to that recalls from pre-calculus, I think, where they teach you that the square root of 1 minus t squared is a circle. Okay, so for this problem, we're just going to believe that it's a circle. Okay, and this circle has the radius of 1. So this line here is 1, and so is this. Okay, being that, in other words, this is a slice of a pie. And then the equation of, well, anyway, so at this point right here, where we're integrating, what are we integrating? We're integrating this whole area, in other words, we're calculating the area under the curve of that whole thing. And this point here is, and we're integrating from 0 to x, holding x constant. So for each x, we'll calculate the area under the curve of the, yeah. So so that this point, if this point is x, then the y value, this point's coordinate will be the y, or the y value is square root of 1 minus x squared, and which is this height. Okay, 1 minus x squared. So the height here is 1 minus x squared, and this and the width here is just x. Now in that case, then the area, we can at least figure out the area of the triangle. The area of the triangle, so I'll write down A of the triangle, okay, just that part, equals the base times height over 2. 1 minus x squared. Now, and check this. That's exactly that part of the answer. So we're already halfway there. Okay. Now, now we are going to calculate the area of this thing. Now, the area of what is the area of that? Then what we're gonna do is calculate. Well, we need to know what this angle is, right? To because the area of a slice of pie is given by the formula theta. Let's say this angle is theta. The area depends on theta. Okay, of any pie slice. Is that a pie? Yeah. A slice of pie is, the area is, let's say you have a slice of pie, okay, and which it has an angle here, which is theta. Its area equals to area of this slice equals to here's the radius, okay, equals to pi r squared, that's the entire circle, and times theta over 2 pi. Oops. Times theta over 2 pi. That's because the whole pie is 2 pi, the whole circle is 2 pi, so the theta part of it is just whatever fraction it is. And in our case, the radius is just 1, so we can simplify this to be pi theta 2 pi. That's the area of our slice here. Okay, and then so next we need to figure out what is theta. To figure out what is theta, we know that this is theta, which by the rules of geometry, so is this. Okay, and more importantly, you notice the sine of theta equals to x. Here's a rule, okay? Sine theta, observation actually, sine of theta, which is opposite divided by hypotenuse, equals to x over 1, which is just x, which means theta equals the sine inverse of x. So that's how you calculate theta. Now, so the area of the pie slice, then we know what theta is. So next, the area of our slice of pie, okay, I'll write it this way, which equal to pi times theta, which is sine inverse of x, divided by 2 pi. Right? And that your pies, these pies cancel out, so it becomes 1/2 sine inverse of x, which is exactly that chunk right there. Okay, and so then now we have finished the proof. So we proved this thing, being that we don't know how the integration. We proved this thing in the roundabout with a roundabout trick. Basically, is how we calculate this one. It doesn't teach integration directly, but I still think this is worthy of doing, and be able to recognize various things like the area can be cut in half and with that, it comes to the end of this section.